ULTEM is an aerospace-grade polymer capable of replacing metal in a wide range of demanding applications. But unlike commodity polymers such as PLA or PETG, ULTEM demands a much more tightly controlled manufacturing process to be successful, which raises an important question. Do I need to spend the extra cash to get a true high-temp system, or can I get by with a lower-cost, lower-temp system? Depending on the answer, you could save over $100,000, or you could spend months redesigning parts, tuning process parameters, and chasing repeatable results. The problem is, manufacturers with build chambers ranging from 80C all the way up to 300C all claim they can print these materials. So here's the obvious question. If all you need is a 120C build chamber to reliably manufacture ULTEM and peak parts, why don't all high-temp 3D printers stop at 120C? Despite using the same underlying ULTEM resin, different filament manufacturers recommend dramatically different chamber temperatures. So who's right? Can you reliably print ULTEM at a 120C build chamber? Or are there hidden trade-offs that don't become apparent until it's too late? This is exactly what we wanted to test, so we set out to answer three simple questions. With a 120C build chamber, can I get my part? How will that part perform? And are those results repeatable across printers, production runs, and different parts? To test this was simple. We printed ULTEM 9085 and ULTEM 1010 in a 120C chamber with a 185C bed. Then we repeated the builds at the recommended chamber temperatures. For ULTEM 9085, we recommend a 185C chamber and bed, and for ULTEM 1010, 210C. First, we wanted to evaluate printability to figure out what could and couldn't be printed at these lower chamber temperatures. Rather than selecting a torture test that exaggerated the differences between systems, we started with a simple geometry, a fully dense rectangular bar. There were no unsupported overhangs, no complex toolpaths, or no intricate features, just a straightforward geometry designed to eliminate as many variables as possible. Even with this simple geometry, both materials warped significantly in the 120C chamber. In fact, we had to add a giant brim, modify the geometry, and use an adhesion aid just to get the parts to stick beyond a few layers. So why did this happen? As the polymer cools, it shrinks. In a properly heated chamber, that cooling is delayed, allowing the part to contract uniformly after the build. In a colder chamber, shrinkage begins almost immediately after deposition, creating residual stresses that eventually warp the part or cause layers to separate. For our next test, we wanted to see how geometry improves printability by reducing stress concentrations. We selected the circular idler pulley because its symmetrical design promotes uniform shrinkage, distributing residual stresses evenly around the perimeter rather than concentrating them at corners. Even then, it wasn't as simple as pressing print. After countless attempts, we still had to modify the geometry. We switched to a concentric base infill, applied an adhesion aid, and reduced the infill to a bare minimum before we could produce a successful part. And even then, the part contained dimensional accuracy issues due to premature cooling. So yes, a 120C chamber is enough to print ULTEM, but with limitations. You're likely going to be spending a lot of time modifying your part and the print settings around the limitations of the machine rather than the application itself. But printability is only half the story. A part that looks great on the build sheet isn't necessarily guaranteed to perform like ULTEM should. So the next question becomes, how much of your mechanical performance is compromised by printing in a 120C chamber? To answer that, we printed ZX tensile bars 5 at a time to replicate the layer times and thermal conditions of a real part. Unlike XY specimens where the load is primarily carried by continuous extruded beads, ZX specimens transfer that load across hundreds of deposited layers. Rather than measuring the polymer's bulk strength, ZX testing evaluates how effectively the printing process manufactured the part. We also annealed some of the specimens to see if we could recoup any of that lost part strength. Lastly, we added in a chain link geometry to see how trends extended beyond non-standardized geometries. So let's take a look. Starting with ULTEM 9085, parts printed at the recommended 185C chamber consistently outperformed those at 120C. Tensile strength increased by approximately 44%, with cold specimens performing on par with polycarbonate, a low-cost engineering-grade polymer. Unfortunately, annealing produced marginal increases in part performance and also resulted in a lot of warping. Equally important to strength, the higher chamber temperature improved ductility and demonstrated far better consistency between samples, which is important because manufacturing isn't just about achieving strength once, it's about producing the same result every time. ULTEM 1010 told a much different story. Printing at the recommended 210 C chamber temperature increased tensile strength by over 200%, more than tripling part strength. To put that in perspective, the 120 C specimens were actually weaker than tough PLA. And when you're paying roughly $200 per kilogram for ULTEM 1010, that's a significant compromise. So, how can chamber temperature alone reduce strength by this much? And why did annealing recover so little of it? The answer lies in the thermal history of the print. Interlayer welding depends on polymer chains remaining mobile long enough to diffuse across the boundary between layers. The chamber temperature needed to preserve that mobility differs by polymer. For amorphous materials like ULTEM, the welding window centers around the glass transition region. For semicrystalline materials like PEEK, the ideal chamber temperature is generally closer to the material's melting and crystallization range. In either case, a hotter chamber slows cooling and extends the time available for strong interlayer welds to form. To visualize this, we used our basis software to run transient thermal simulations of the build process, comparing parts printed at 120C with parts printed at 185C chamber. As you can see, on the 185C chamber, the entire part remains warm throughout the build, extending the welding window for each newly deposited layer. When we look at the 120C chamber part, you can see that the surrounding material cools much more quickly. By the time the nozzle returns for the next layer, much of the previous layer has already cooled beyond the effective welding window. This simulation also shows how the hotter 185C bed helps compensate for colder chamber temperatures, but only to a certain point. Once the geometry extends beyond that thermal threshold, printability drops off rapidly, making it increasingly difficult to manufacture successfully. This is why annealing was not an effective substitute. By the time the part has cooled, the critical window for developing strong interlayer welds has already passed. In short, the best time to develop strong interlayer welds is during the printing process, not after the part has cooled. Looking at the fracture surfaces, we can see the consequence of poor welding firsthand. On the left, the ULTEM 1010 specimen printed in the 120C chamber failed perfectly along the layer boundaries. At the recommended chamber temperatures, fractures propagated through dozens of layers, showing that the interfaces were no longer acting as the dominant weak points. Now that we've covered the physics of what's going on, the obvious question becomes, how am I seeing successful ultimate PEEK parts printed on these 120C chambers? And can I design around those limitations? To some extent, yes, but only if you're willing to devote a significant amount of time tuning the process to each individual part, and your designs are flexible enough to accommodate those modifications. In short, those modifications fall into two primary buckets: keeping your layers warm enough for long enough to form strong interlayer welds, and managing stress concentrations as the part cools during the build. The first challenge is keeping each deposited layer hot enough for long enough. When printing in 120C chamber, this is done by reducing layer times. So printing very small parts, printing thin weld parts, reducing infill, or printing low profile parts that stay within the bed's thermal threshold. Unfortunately, there's no silver bullet here. Every new geometry and every design modification is going to come with its own unique set of challenges that you need to adjust for. Earlier, we mentioned that geometry determines where shrink forces develop, and this is where design changes become essential. Rather than eliminating shrinkage, you'll need to distribute those shrink forces over a larger area. Sharp corners and abrupt transitions concentrate that shrinkage in a single location, making them much more likely to warp or crack. Instead of corners, you'll want to use fillets, chamfers, rounded features, and simplify the geometry to spread those shrink forces throughout the part, making them significantly easier to manufacture. The trade-off, of course, is that you're no longer designing around the part and its functional requirements. you're now having to design around the limitations of the manufacturing process. So the third and final question we set out to answer is the process repeatable? The issue isn't whether you can eventually make a part print. The issue is the amount of engineering required to get there. At 120C, every new geometry, every design change, or process adjustments often require another round of tuning just so you can get a successful part. Instead of rapidly manufacturing new designs, engineers are often forced back into process development, modifying the design, tuning print parameters, and printing multiple iterations before arriving at an acceptable result. For a handful of parts, that trade-off might be acceptable, but for most, that level of process development quickly becomes impractical. So, just to sum everything up, everything we've shown you in this video is not based on theory. Here at Aeon 3D, we launched our first printer over a decade ago with a 70-seat chamber. At the time, our maximum chamber temperature was dictated by our ability to cool components inside the build chamber, a limitation imposed by design patents at the time. Over the next decade, we learned the challenges and limitations of printing in colder environments, and those experiences helped shape our next generation platform. With a thermally optimized 250C build chamber, Hilo dramatically widens the processing window, making it easy to manufacture parts successfully on the first try, even with complex geometries and the most difficult to print high-performance polymers. Combined with end-to-end automation and multi-physics-driven process tuning, Hilo replaces trial and error with a predictable, repeatable manufacturing process. In closing, if you're shopping for a high-temp 3D printer, don't just ask if a system can print ULTEM or PEAK. Ask if that printer can print your designs with the properties your applications require, reliably, repeatably, and without compromise. To learn more about Hilo, visit aeon3d.com. And if you found this video helpful, don't forget to like and subscribe to follow along for more engineering deep dives into high-temperature additive manufacturing.